So welcome everyone to this beautiful channel named Inspire Chemistry, created by my friends Amit Kumar Ghoshal and Aditya Bharadwaj, who are with me at JNC. So to start with, I am an MSc student. My name is Anastu Mukherjee and I am at JNC itself. So I guess I have been introduced in this channel in the previous video, and I am here to explain some aspects of quantum chemistry or quantum mechanics, and I will be happily answering all your questions if I could. So let's start with so the topic is quantum mechanics, and or more precisely we will learn what is quantum chemistry. So as I told you that we will learn this topic with a series of lectures on it, but why do we need to learn this actually? So what is the need of this theory, quantum mechanics, not in our day-to-day life but to understand various phenomena also. So to begin with, we know that classical mechanics, or in other words Newtonian mechanics, explains relatively everything in our day-to-day life, like we walking on the road, a rocket going into space, etc. And many more things are there which can be explained by Newtonian mechanics or classical mechanics. So why do we need quantum mechanics then? So if this theory exists, then there should be some phenomena which could be explained, or which are explained by this theory and not the previous one which I was talking about, or say classical mechanics. So there are some observations or experimental facts and experiments as well which are explained by quantum mechanics and not by classical mechanics. And to begin with, the first topic is blackbody radiation. So let us first dissect the term itself. So first term is blackbody, and the second term is radiation. So what is a black body? A black body is one which emits and absorbs at all possible frequencies. To generalize, and this is what is black body, and if I say radiation, it's something to do with light coming from it or light absorbed in it. So I guess you guys have seen when a rod is heated, it first turns dull red, then it turns dark red. If the rod is further heated, or in other words, if the temperature is further increased, the rod becomes white, as well as if it is further heated, it becomes blue as well. So in terms of frequency, there is a shift from red to blue. That is from lower frequency to higher frequency, and this gives us a spectrum. And this spectrum gives us a spectrum, and this spectrum will be system dependent. So in order to we can't deal with every possible system, so in order to generalize the fact that is happening in such a phenomena, we take what is called black body, which serves the purpose for understanding what is going on in this. So black body serves the purpose of understanding this spectrum, and there are two characteristics to this spectrum. One is the Stephen-Boltzmann's law. Which is given by this equation where R is the power emitted per unit time, or is also known as the excitance, and it is the power emitted per unit, sorry, it's not time, it's area of the emitted region. This is the average energy density, and C is the speed of light. Sigma is known as the Stephen-Boltzmann constant, and T is the absolute temperature of the system. So this is a constant, C by 4 is a constant. So the average energy density depends on fourth power of the temperature, and the other characteristic feature of this is the Wien's law. So this average density can be written in terms of wavelength and temperature. This is frequency. So Wien's law states that lambda max, or it's not exactly the maximum wavelength, it is the wavelength at which the highest absorbance occur or the highest intensity is observed, is inversely proportional to the temperature of the system. And the plot for this looks like, the spectrum I was talking about looks like So the spectrum looks like this, and these are the temperatures. With the increase in temperature, the average energy density or the intensity of this increases. So, and this constant, exactly, I missed it. This constant is actually given by where h is the Planck's constant. I will come to this, how it comes. C is the speed of light. This is a constant, as it is a number, and kV is the Boltzmann constant. So don't worry about these things. We will deriving these equations also. So let's come to the fact that this theory came into existence. Okay, so which means that the classical mechanics or the classical theory of electromagnetic radiation failed to explain this phenomena. So in order to explain this spectrum, two scientists, Rayleigh and Jeans, came up with a law for the average energy density, which is given by So the relative energy density between the frequency, or the radiative energy density between the frequency nu to nu plus d nu is given by this equation. So I will tell you about one fact. I will derive this, so don't worry about how it comes. But this Rayleigh-Jeans law fits considerably well for low frequency region of the spectrum. So if you have the experimental data and substitute this, you will considerably satisfy this region of the spectra, because this goes as nu square. It's the second power of frequency, and thus the graph corresponding to this will look like this. And the second scientist who came up with the idea, or rather I should say with an equation, it's Wiens himself. Wiens himself, who gave the equation in terms of wavelength as this. And the expression looks like this. So if you look into this, he derived it in terms of wavelength. Rayleigh-Jeans also derived in terms of wavelength, but I feel comfortable to write it in terms of frequency. So Wiens came up with this, and this with the experimental data fits good for low wavelength region or high frequency region. So scientists in the late 90s have tried fitting that curve or the spectrum I showed you, but could not succeed with the classical theory of electromagnetic radiation. So a brilliant theoretical physicist came up with an idea, and his name is Max Planck. He actually saw that as Rayleigh-Jeans law fits good for low frequency and Wiens law fits good for high frequency, he came up with an equation for the same purpose, or for the same thing, the radiative energy density given by this equation. So if you look at this, if the wavelength is high, if lambda is large, if the wavelength is high, or in other words lambda is large, this term, which is b by lambda t, would be small, and the exponential term can be expressed as or approximated as if you look at this, if the wavelength is large, the frequency is low, and the exponential term can be written as this. And substituting this and this, what we get is where A and B are constants, and its inverse 4 power of wavelength. I told you that Rayleigh-Jeans derived the equation in terms of wavelength, and which looks exactly similar to this. The constants are still needed to be derived. I will do that one also. So, and the second condition, if the wavelength is small, then d by lambda t is large, and exponential of that term is even larger. Thus, exponential b by lambda t is much greater than 1, and this reduces to this, which is the exact form of Jeans law. So, what was Planck's actual idea? How did he came up with this expression? Okay, we know that he saw that Rayleigh-Jeans law fits good for the low frequency region, and Jeans law fits good for the high frequency region. But what he suggested that that the radiation generated in the system is due to vibrations of electrons of the constituent particles of the system, and those vibrations are quantized, which means that the energy cannot take up any possible value, which is the main aspect of classical mechanics, that it can take up any possible value. Is it continuous? If we look at the energy spectrum, it's continuous for classical mechanics, but for this the energy is quantized, and he assumed that the energies is in the form of this, where energy of any particle is integral multiple of some energy, which is the smallest value, or he came up with this. X is an undetermined constant. When all the experiment data is fitted into this expression to obtain A, B, after obtaining all this, he saw that H is what is now known as the Planck's constant, and H has the value 6.626 into 10 to the power minus 34 joule second. Now, this is the gist of the system. Blackbody radiation could not be a phenomena which was not explained by classical mechanics or the classical theory of electromagnetic radiation. So, scientists like Rayleigh-Jeans and Jeans came up with expressions for the average energy density of the system, and their expressions fitted the absorption spectrum originally obtained for the whole lot of experimental data in some regions of the spectrum. But if you look in case of Planck, a brilliant theoretical physicist, uh, obtain an expression combining, obviously considering both the way the Rayleigh-Jeans and Wiens have obtained their expression and have fitted some parts of the spectrum, have obtained a term which fits the complete spectrum beautifully. So in order to, I told you that I will derive the Rayleigh-Jeans formula. Wien's formula is what I will not derive. I wish you could find some derivations for this. This is and share with us also, because this is a very good expression. Sorry. So let us derive the Rayleigh-Jeans law. And one thing to be noted, that Rayleigh-Jeans and Wien use classical theory of electromagnetic radiation to obtain these expressions of rho lambda T. So if we look into the system, suppose this is a black body with a pinhole in it. The radiation can come out of this. This is what we will observe. This is the detected radiation. This is the detected radiation, and this comes after many reflections and reflections and reflections of the system. And so on. So it's something like, if you have a system and light has entered in it, it will go reflections and re-reflections in order to equilibrate it, in order to come in thermal equilibrium. In order to derive what Rayleigh-Jeans have derived in their expression for the average energy density, this is a system. This is the basic system through which we can explain this. And if you look that these are of fixed lengths, so it can be thought that the radiations form what is called standing waves. And the basic form of basic equation which explains standing wave is something like this. This is a sphere. It can be a cube also. In considering a cube, this is the length of the cube. This is any integer, positive integer from 0, 1, 2 and so on. And this is the half wave cycle, that is half of the wavelength. So we know this. So wavelength comes out to be 2L by N, and the frequency corresponding to this is this. Now in order to obtain the expression, let us say or define something which is called wave number. So this is the wave number. Substituting what is lambda in this, we get or converting this to frequency terms, something like by C, and substituting nu or the frequency in this, what we obtained is pi n by L. Okay, so this is the expression of the wave number, and it is given by this. I'll tell you why I am squaring it. Let us just square this. So is n square. So if we define a 3-dimensional system as I have defined L to be the length of the cube, then in all the possible, there are 3 directions only. So in these 3 directions, we can write or taking this expression into prime account, is this, and this is the prime equation, and we also know that Q is given by this. Q is given by this. So substituting this here will give 4 pi square mu square c square pi square L square, which is equal to 4 mu square L square by c square. So this is the equation, this is the expression, this is the expression obtained for nx square plus ny square plus nz square to be equal to this. Now, if you look into this carefully, nx square plus ny square is plus nz square is some constant for constant mu and n, and thus can be considered as an equation of a sphere. So sphere of radius so this is the equation of a sphere, and the radius is given by this. So if I look into this is actually R, and this is the sphere. What we need to do is just extend it a little, and this is something called dr. So we need, in order to find the combinations of nx, ny and nz which satisfies the equation, we need what is called the area of the strip, or the area of the spherical shell. Now, volume of the sphere is given by V equal to 4 by 3 pi r cube. We all know this. And the derivative, or the small volume element dV, is given by r square dr. We have written the expression for r as and this is also equal to this. So thus from this, what we obtain in the change in the small radius is this, and thus substituting the value of r here and substituting the value of dr here, what we finally obtain So this is the expression obtained for the small volume element dV. But we need to consider a thing that I wrote in the starting of this derivation, that n lambda by 2 is equal to the length of the side edge of the cube, and I said that n should take only positive integer values. So if I take a sphere and set up a coordinate system at x, y and z, the possible combinations of nx, ny and nz are obtained just for one octant of the Cartesian coordinate system. So 1 by 8 of the volume element will give me something like this, and something like this, and this is also equal to the number of non-negative combinations. As I have said, that we have to take 1/8 of the octant for the sphere, and this is equal to dn, or in terms of wavelength, if you want it, this looks like so. If you look into the equation carefully, you are getting something like mu square, and you are getting something like dn also. So this is not the exact thing what we want, but you are getting a gist of that. In the Rayleigh-Jeans expression, there is a mu square dependence, and that is coming here right now. So if you look into this thing more carefully and go on with the further derivation, this system will look something like this actually. So one thing to mention here, that in the Blackbody radiation, the radiation emitted is by the electrons of the constituent particles, and the electrons act as harmonic oscillators. So you know by your you just remember this for a while, that for a harmonic oscillator system, the average of kinetic energy, or I should not use this symbol actually, the average of kinetic energy is average of potential energy. And the classical theory of electromagnetic radiation says that the average of kinetic energy is half kBT, which is where kB is the Boltzmann constant and T is the temperature of the system. So the total average energy is kBT. Okay, so this is the thing you need to remember, because in Planck's derivation, which we will cover, the only thing that changes is actually this. This is the thing which differentiates Planck's derivation from Rayleigh-Jeans and Wien's also, because this energy value can take up any value depending on the temperature. But this is not the case, as I explained, that Planck took that the energy can have only certain discrete quantized values. So how this equation is important here is something like this. If we look into what is called the average energy or the average radiative energy per unit frequency, which has an expression like this, is given by kB time T, where this is the average energy actually, dN by dU. Oh, I have erased the dN term, and it actually looks like so. This is dN, and dN by dnu is this. So if you substitute this expression into this, then the average radiative energy per unit frequency will look like so this is the term, this is the expression for the average energy per unit frequency. If I want the average energy density, then I need to divide it with the volume element, which is L cube actually. So this expression converts to So this is the expression for the average energy density per unit frequency. And if one more thing to add into this is the light, that is the radiation coming from the system, is not polarized in one direction, it's polarized in two directions, and taking that polarization factor into account, this term actually converts to 8. So you need to keep this in mind, that the polarization factor involves a multiplication of of 2 with this term and gives this. So basically this is the Rayleigh-Jeans law. So if you look into this expression, this is what matches with the expression I wrote previously in terms of frequency and temperature to be this, and in terms of wavelength, this is something like so. You will get this expression in many books because they feel it is good to explain in terms of wavelength, but I feel comfortable to write in terms of frequency. So this is how the Rayleigh-Jeans law is obtained, and I should stop here. I have given you the basic gist of what is called blackbody radiation, what happens, what is the consequence, why quantum mechanics, why Planck has come up with the brilliant idea of energy quantization, that is, the energy can have only certain discrete values, and this is the expression which is obtained. In other words, I have derived what Rayleigh-Jeans have derived previously. I have given you Wien's contribution also, and both these Rayleigh-Jeans and Wien's combined, Planck used an expression for the average energy density, and I have shown you that equation also. So now the basic thing will be that I have also showed you that the expression given by Planck with the unknown constants, the constants will be determined. So with the unknown constant reduces to Rayleigh-Jeans law in the low frequency or high wavelength region, and reduces to Wien's law in low wavelength and high frequency region. So thank you for watching this, and please do like, subscribe and comment, and I will be glad to answer questions that are posted on this channel, that are posted on this video. And thank you so much, and I will continue with this. I will continue with the Planck's derivation also, and I will explain the two characteristics that I have told you, the Stephen-Boltzmann's law and the Wien's law from the Planck's equation. And thank you so much.